Nothing. What is it? Is nothing merely the absence of everything, a void devoid of substance and meaning? Or does it hold a profound significance, perhaps serving as the canvas upon which existence itself is painted? In massiveness of space, amidst shining galaxies and devouring black holes, lies a perplexing concept: nothing. Picture a corner of space where there's almost nothing. No stars, no planets, just emptiness. It's like a quiet pocket where the laws of physics seem to take a different shape. Where did the emptiness come from? Join us as we venture into this mysterious emptiness, where we'll travel through space, discover the latest technology, and unlock the secrets of nothingness. In the expanse of the universe, the concept of nothing might seem simple at first glance: empty space, devoid of matter or energy. However, in a cosmological context, nothing is far more complex and intriguing. Scientists argue that even the emptiest parts of space are filled with a seething, bubbling froth of virtual particles that pop in and out of existence. This idea stems from the principles of quantum mechanics, which suggest that nothing, or the vacuum of space, is not truly empty, but rather a field of endless potential. These virtual particles, though fleeting, can have genuine physical effects, hinting at a universe that is vibrant even in its most desolate voids. Furthermore, the theory of cosmic inflation posits that our entire universe could have burgeoned from a vacuum fluctuation, a kind of nothing bursting into everything. This challenges our understanding and perceptions, pushing us to think beyond traditional notions of emptiness or void, and into a realm where nothing is a dynamic, foundational component of cosmology itself. According to the principles of modern physics, the notion of nothing as a complete void or absolute emptiness is a concept that's more philosophical than scientific. Quantum mechanics, a fundamental theory in physics that describes the physical properties of nature at the smallest scales, suggests that nothing in the strictest sense doesn't exist. This is because the vacuum of space, what one might consider the closest thing to nothing, is actually teeming with energy and particles that flash into and out of existence. These particle-antiparticle pairs, known as virtual particles, pop up and vanish too quickly to be observed directly, but have tangible effects that physicists can measure. Physics further complicates the idea of nothing with the Heisenberg uncertainty principle, which implies that there is a fundamental limit to the precision with which certain pairs of physical properties, like position and momentum, can be known simultaneously. This principle suggests that even in what we might think of as a perfect vacuum, there are intrinsic uncertainties that prevent it from being truly nothing. In this light, physics paints a picture of a universe where nothing in its purest form is an abstract, perhaps unreachable concept, hinting at the rich and complex underpinnings of our reality. The concepts of space and time hold a pivotal role in understanding the universe's beginning, an event encapsulated in the theory known as the Big Bang. This grand event, which took place around 14 billion years ago, marks the inception not only of all matter and energy, but also of space and time themselves, as we understand them. In the singularity from which the universe sprang, all the universe's contents were infinitely dense and converged into a point of zero volume, meaning that concepts of space as we understand them did not exist prior to the Big Bang. Similarly, time as a measurable progression could not have commenced until the universe began to expand. The theory of general relativity, introduced by Albert Einstein, fundamentally ties the fabric of space to the flow of time, suggesting they are interwoven into a four-dimensional continuum known as spacetime. This concept implies that before the Big Bang, since there was no space, there could not have been time as we perceive it. This leads to fascinating and somewhat paradoxical implications for the beginning of the universe, positing that the notions of before the Big Bang might not make sense in the way we typically understand time. Thus, the origins of the universe challenge our perceptions, indicating that the birth of the cosmos was also the birth of the very stages upon which all cosmic events play out, space and time itself. The speed of light, approximately 300,000 kilometers per second, holds profound significance in understanding the universe's origins and the fabric of cosmic reality. One of its pivotal roles is acting as the ultimate speed limit of the universe, a fundamental principle established by Albert Einstein's theory of relativity. This principle means that nothing can move faster than light, setting a boundary on how quickly information and matter can travel through space. This has intriguing implications for our understanding of the universe's size and age. Since light from distant galaxies takes billions of years to reach us, we're essentially looking back in time when we observe these far-off reaches of the universe. Thus, the constant speed of light allows astronomers to map the universe's history and structure, giving us a glimpse into the state of the cosmos shortly after the Big Bang. Moreover, the speed of light underpins the concept of the observable universe, defining the limits of the cosmos that we can see. Anything beyond this limit is unreachable within the age of the universe due to the finite speed at which light travels. Consequently, the speed of light not only dictates the fundamental structure and dynamics of the universe, but also frames our understanding of its very origins, making it a cornerstone in the quest to comprehend the cosmos. Cosmologists endeavor to unravel the mysteries of the universe's origins, a quest that is as exhilarating as it is fraught with challenges. One of the most significant challenges is the limitation imposed by the observable universe. The speed of light, while incredibly fast, means that there is a horizon beyond which we cannot see because light from there has not had enough time to reach us since the beginning of the universe. This limitation means that portions of the universe's early history are inaccessible to us, cloaked forever in mystery. Another formidable challenge is the interpretation and understanding of the cosmic microwave background radiation, the afterglow of the Big Bang. While this radiation provides a wealth of information about the early universe, deciphering its subtle fluctuations requires sophisticated technology and complex mathematical models. Cosmologists also grapple with the enigmatic nature of dark matter and dark energy, which constitute most of the universe's mass energy content. These invisible entities influence the universe's evolution and structure, but evade direct detection, making their study both intriguing and exasperating. Additionally, the extreme conditions of the universe's infancy, such as the high energy levels beyond the reach of current particle accelerators, mean that some aspects of the Big Bang theory and its aftermath can only be probed indirectly through astrophysical observations. The Big Bang theory, a cornerstone of modern cosmology, describes the universe's origin as an expansion from an infinitely dense and hot state, rather than conjuring the universe from nothing in the philosophical sense. At its core, the theory posits that roughly 14 billion years ago, the universe started expanding from a singularity, a point of zero volume and infinite density, where the laws of physics as we know them cease to operate. This explosive expansion filled the universe with the primordial heat and energy from which all matter eventually formed. However, the concept of nothing preceding the Big Bang touches on deeper, unresolved questions in physics and cosmology. The singularity from which the universe is thought to have emerged comes from general relativity, which breaks down under these extreme conditions, leaving a gap in our understanding of how the transition from nothing to a singularity and then to an expanding universe might have occurred. Quantum theories of gravity, still in development, hint at a pre-Big Bang scenario or suggest that singularities might not even exist within the framework of the universe, implying a different concept of nothing. The Big Bang theory elegantly explains the observable characteristics of the universe, its vast expansion, and the cosmic microwave background radiation, Yet the mystery of what preceded the singularity, or how nothing transitioned to something, remains one of the most profound puzzles at the heart of understanding our origins. The Big Bang Theory, the predominant cosmological model describing the early development of the universe, is supported by several key pieces of evidence. Firstly, the observable expansion of the universe provides a strong foundation for the Big Bang Theory. Edwin Hubble's observation in the 1920s that galaxies are moving away from us in all directions suggests that the universe was once concentrated into a very dense and hot state from which it has been expanding. This expansion implies that the universe had a beginning, a singularity, from which it has been spreading out. Secondly, the cosmic microwave background radiation discovered in 1965 by Arno Penzias and Robert Wilson serves as a relic of the universe's early hot and dense state. This faint microwave radiation permeating the universe is a snapshot of the aftermath of the Big Bang, acting as a cosmic echo of the universe's infancy. Thirdly, the abundance of light elements such as hydrogen, helium, and traces of lithium predicted by the Big Bang nucleosynthesis model corroborates the theory. These elements were formed during the first few minutes after the Big Bang in a process called nucleosynthesis, and their observed abundance throughout the universe matches theoretical predictions. These foundational elements, along with the structure formation of the universe, including the distribution of galaxies and the cosmic web, further support the Big Bang theory, providing a comprehensive explanation for the universe's origins and its subsequent evolution. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the CMBR is the afterglow of the universe's infancy, a remnant from a time about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral atoms, making it transparent to radiation for the first time. This ancient light, stretched to microwave wavelengths by the expansion of the universe, provides a snapshot of the universe at this critical juncture in its evolution. The uniformity of the CMBR across the sky, with slight fluctuations, reveals essential clues about the early universe's structure and the distribution of matter. These minute temperature variations, mapped by satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft, are the seedlings from which galaxies and large-scale structures eventually grew. Analyzing the CMBR also helps cosmologists determine the universe's age, composition, and rate of expansion, offering precise constraints on models of the universe's development. Thus, the CMBR not only underscores the validity of the Big Bang theory, but also serves as a cosmological Rosetta Stone, deciphering the early universe's conditions and guiding our understanding of its origins. Following the Big Bang, the universe underwent a rapid expansion and cooling process, setting the stage for the formation of the first elements, an epoch known as Big Bang nucleosynthesis. In the initial moments after the Big Bang, the universe was an extremely hot and dense plasma of quarks and gluons. As the universe expanded and cooled, these fundamental particles combined to form protons and neutrons within the first minute. During the first few minutes of the universe, the temperatures and densities were conducive to nuclear reactions, wherein protons, hydrogen nuclei, and neutrons began to fuse together to form heavier nuclei, marking the dawn of element formation. The sequence of these nuclear fusion reactions led to the creation of the lightest elements. Firstly, deuterium, an isotope of hydrogen, was formed from protons and neutrons coming together. Deuterium nuclei then fused into helium-3. Some of the deuterium and helium-3 further combined to create helium-4, the universe's second most abundant element after hydrogen. Tiny amounts of lithium and beryllium were also produced during these initial minutes. After the first 20 minutes, the universe cooled to the point where these nuclear reactions effectively ceased, freezing the abundances of these light elements. The proportions of these primordial elements, roughly 75% hydrogen and about 25% helium by mass, with trace amounts of lithium and beryllium, match remarkably well with predictions from Big Bang nucleosynthesis models and with what is observed in the most ancient and distant galaxies. This agreement between observation and theory concerning the primordial abundances of light elements provides strong evidence for the Big Bang theory and enhances our understanding of the early universe's conditions, leading to the formation of the first elements. The horizon problem in cosmology refers to the question of how regions of the universe that are far apart and should not have been able to exchange information due to the speed of light limit appear to have the same temperature and density. This observation contradicts the expectation that, given the vast size of the universe and its age, different regions should exhibit significant differences in these properties. Current cosmological theories address this conundrum primarily through the concept of cosmic inflation. Cosmic inflation is a theory that proposes a period of extraordinarily rapid expansion of the universe immediately following the Big Bang. According to this theory, a tiny fraction of a second after the universe's birth, it expanded exponentially, much faster than the speed of light, for a brief period. This dramatic expansion would have stretched out any initial irregularities or differences in temperature and density, leading to a universe that appears remarkably uniform on large scales as we observe today. Inflation, therefore, solves the horizon problem by ensuring that even regions of the universe, presently too far apart to have been in causal contact, have originated from a small, causally connected volume in the early universe. Moreover, inflation predicts the existence of very slight variations in the temperature and density of the cosmic microwave background radiation, which have been observed by instruments such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. Quantum fluctuations are temporary changes in the amount of energy in a point in space, as predicted by the uncertainty principle of quantum mechanics. This principle states that there are inherent uncertainties in measuring both the position and momentum of particles, leading to fluctuations that allow particles and antiparticles to appear spontaneously out of the vacuum, provided they annihilate each other quickly and do not violate the conservation of energy over time. These fleeting occurrences are not merely theoretical constructs, but have observable consequences, such as the Casimir effect, which demonstrates their physical reality. In the context of the universe's origin, quantum fluctuations play a crucial role in theories about the very early universe, particularly during the period of cosmic inflation. According to inflationary theory, the rapid expansion of the universe was driven by a scalar field known as the inflaton field. Quantum fluctuations in this field could have been stretched to macroscopic scales by the inflationary expansion, seeding the inhomogeneities that later grew into galaxies and large-scale structures in the universe. Essentially, these minute quantum fluctuations, when magnified across the cosmos, provided the initial irregularities needed for matter to clump together under gravity. Additionally, some theories propose that the universe itself could have originated from a quantum fluctuation in the vacuum of a pre-existing space or universe, suggesting that our entire cosmos could be the product of quantum mechanics on a grand scale. While this idea is speculative and remains a subject of intense research and debate, it underscores the importance of quantum fluctuations not only in the shaping of the cosmos's large-scale structure, but also potentially in its very genesis. Quantum fluctuations exemplify the intersection between quantum mechanics and cosmology, highlighting the profound and often surprising ways in which the micro-scale world of particles influences the grandest scales of the universe. According to quantum theory, the concept of the universe arising from nothing can be understood through the framework of quantum fluctuations, which are temporary changes in energy in a region of space due to the uncertainty principle. In the realm of quantum mechanics, empty space is not truly empty, but rather a seething foam of virtual particles that constantly pop in and out of existence. These virtual particles are pairs of particles and antiparticles that briefly appear together, separate, and then come back together to annihilate each other, disappearing without violating the conservation of energy over short timescales. This phenomenon suggests a universe that can spontaneously arise from a quantum vacuum state, where a fluctuation of the right magnitude could have sparked the creation of the universe as we know it. In this scenario, under the right conditions, a quantum fluctuation could have provided the initial energy for the Big Bang, leading to the rapid expansion and cooling that mark the beginning of our universe. The laws of quantum mechanics allow for such fluctuations, and although starting a universe in this way might seem improbable, it is not outside the realm of possibility according to the current understanding of physics. Furthermore, models incorporating quantum mechanics and general relativity, such as the Hartle-Hawking state, propose that time itself could have emerged from such a quantum state, smoothing the transition from nothing to a universe filled with matter and energy. These theories suggest that, rather than picturing a singularity from which the universe sprang, the early universe should be understood in terms of quantum mechanics, with the cosmos appearing from a state devoid of matter, energy, and even the space-time fabric itself in any conventional sense. Thus, quantum theory provides a fascinating perspective on how the universe might have arisen from nothing, illustrating the profound implications of quantum mechanics for our understanding of the universe's origins. Virtual particles are a fundamental concept in quantum field theory that play a crucial role in theories of the universe emerging from nothing. These particles are transient fluctuations that appear and disappear in the vacuum, the quantum state perceived as empty space. Despite their ephemeral nature, virtual particles can have real, observable effects, such as the Casimir effect, which demonstrates the physical force exerted by these particles. In the context of the universe's emergence, virtual particles offer a mechanism by which the universe could have originated from a quantum vacuum, a state of nothing in the conventional sense. According to this perspective, a vacuum isn't empty, but teems with activity, with pairs of particles and antiparticles continuously popping into existence before annihilating each other. Under certain interpretations of quantum mechanics, these fluctuations could trigger the birth of a universe. A particularly potent fluctuation might not annihilate immediately, but instead could unveil energy that kickstarts the Big Bang, leading to the universe's rapid expansion from a singularity. This framework suggests that the laws of quantum mechanics allow for the creation of the universe from the quantum vacuum, circumventing the traditional notion of creation from absolute nothingness. Virtual particles embody the idea that even what we consider a vacuum is filled with potential, offering insights into the early moments of the universe and the initial conditions that could lead to the cosmos as we observe it today. Thus, virtual particles lie at the heart of modern cosmological theories, exploring the universe's emergence from nothing, highlighting the profound intersections between quantum mechanics and cosmology. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, posits that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. This principle has profound implications for our understanding of the beginning of the universe, particularly in the context of the conditions that might have prevailed at the very moment of the Big Bang. One implication of the uncertainty principle for the universe's beginning is that it suggests a limit to the predictability and determinism of the early universe's state. At extremely small scales and high energies, like those that would have existed at the beginning of the universe, the uncertainty principle implies that energy and space-time would have been subject to fluctuations. These quantum fluctuations could have led to the spontaneous appearance of particles from nothing, potentially offering a mechanism by which the universe, or the energy that fueled its initial expansion, could emerge from a quantum vacuum. Furthermore, the uncertainty principle challenges the notion of a singularity, a point of infinite density and temperature, as the starting point of the universe. Instead, it suggests that the concept of a singular beginning to spacetime may not be applicable or meaningful, as the quantum fluctuations governed by the uncertainty principle introduce a degree of fuzziness or indeterminacy to the conditions at the universe's inception. This fuzziness could hint at a pre-Big Bang state or scenarios where conventional notions of time and space break down. Thus, the uncertainty principle not only deepens the mystery surrounding the universe's origins, but also provides a conceptual framework that supports the exploration of theories beyond the classical Big Bang model. By highlighting the inherent unpredictability and instability of the early universe's quantum state, the uncertainty principle opens the door to understanding the cosmos's birth in fundamentally new ways, grounded in the principles of quantum mechanics. Quantum mechanics, a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles, has profoundly challenged our traditional views of space and time, particularly when it comes to understanding the universe's inception. In classical physics, space and time are seen as separate and absolute entities, a stage where events unfold. However, at the quantum level, this distinction begins to blur. One of the most striking examples is the phenomenon of quantum entanglement, where particles become interconnected in such a way that the state of one, no matter the distance, instantly influences the state of another. This suggests a level of connectivity and interaction that doesn't quite fit into our classical understanding of space as simply the distance between 2 points or time as a linear progression. Furthermore, quantum mechanics introduces the idea that at the very beginning of the universe, during the Planck Epoch, the first 10 to the negative 43 seconds after the Big Bang, the concepts of time and space, as we understand them, did not exist. They emerged from a singularity, a point of infinite density and temperature, where the laws of physics as we know them break down. This challenges our traditional Newtonian views in a way that forces us to rethink not just the nature of space and time, but the very workings of the universe at its inception. Cosmic inflation is a theory that proposes a period of extremely rapid exponential expansion of the universe shortly after the Big Bang. This event is believed to have occurred within the first tiny fraction of a second of the universe's existence, around 10 to the negative 36 seconds after the Big Bang, to be more precise. The significance of cosmic inflation lies in its ability to explain several crucial puzzles in cosmology. For one, it provides an explanation for the universe's remarkable uniformity. Despite vast distances, different regions of the universe have a remarkably consistent temperature and density. Without inflation, it would be difficult to account for this homogeneity, as these regions could not have been in causal contact with each other to equalize their properties in the time available. Moreover, inflation theory helps to explain the observed distribution of galaxies and the large-scale structure of the cosmos. The rapid expansion would have stretched out tiny quantum fluctuations in the early universe, laying down a kind of blueprint for the later formation of galaxies and clusters of galaxies. Additionally, cosmic inflation predicts a flat geometry for the universe, in line with observations of the cosmic microwave background radiation. In essence, the concept of cosmic inflation is significant because it provides a cohesive framework for understanding the universe's early development, solving several long-standing problems in cosmology and aligning closely with observational evidence. The flatness problem in cosmology refers to the question of why the universe appears to be so close to geometrically flat, meaning the total energy density of the universe is very close to the critical density needed to achieve this flatness. Before the advent of cosmic inflation theories, this observation posed a significant dilemma. The natural expectation was for the universe to deviate significantly from flatness unless its initial conditions were finely tuned to an implausible degree. cosmic inflation provides a compelling resolution to the flatness problem by proposing that an extremely brief but exponentially rapid expansion of the universe occurred shortly after the Big Bang. During this period of inflation, any initial curvature of space would have been stretched out to such an extent that the universe would appear flat on scales smaller than the observable universe. It's akin to how the surface of the Earth appears flat over small distances despite its global curvature. Inflation stretches the fabric of the universe, making any existing curvature so gentle that within the observable universe it's undetectable and appears flat. This stretching also means that the density of the universe would be driven very close to the critical density, naturally explaining why the current density of the universe is so close to this critical value for flatness. Thus, cosmic inflation elegantly solves the flatness problem by eliminating the need for fine-tuning initial conditions, making a flat universe a natural outcome of the inflationary process. The theory of cosmic inflation, while a groundbreaking concept, rests on a foundation of observational evidence that supports its tenets. One of the most compelling pieces of evidence comes from observations of the cosmic microwave background (CMB) radiation. The CMB is the afterglow of the Big Bang, a nearly uniform radiation field permeating the universe. The minute fluctuations in the temperature of the CMB are thought to reflect the density variations in the early universe that would eventually lead to the formation of galaxies and large-scale structures. These fluctuations, as mapped by satellites such as the Cosmic Background Explorer, (COBA), the Wilkinson Microwave Anisotropy Probe, (WMAP), and the Planck spacecraft, match the patterns predicted by cosmic inflation theories remarkably well, providing strong support for the model. Another pillar of evidence for cosmic inflation is the large-scale structure of the universe. The distribution of galaxies and galaxy clusters across vast distances exhibits a pattern that can be traced back to the quantum fluctuations in the very early universe, which were magnified by the inflationary expansion. This pattern fits closely with the predictions made by inflationary models. Furthermore, the confirmation of the universe's flat geometry through measurements of the CMB's anisotropies adds another layer of support for cosmic inflation. A flat universe is a natural outcome of the rapid expansion proposed by inflation, aligning observation with theory. Lastly, the discovery of B-mode polarization patterns in the CMB by experiments such as BICEP-2 can be seen as evidence for gravitational waves produced during the inflationary epoch, although interpretations of these findings are still under scrutiny for confirmation. These observations collectively strengthen the case for cosmic inflation, providing a coherent explanation for the universe's initial conditions, structure, and evolution that aligns closely with empirical data. Variations in the cosmic microwave background, CMB. Radiation are a pivotal piece of evidence supporting the theory of cosmic inflation. The CMB, essentially the afterglow of the Big Bang, blankets the cosmos in a nearly uniform glow of microwave radiation. However, it's the slight variations in this background radiation, known as anisotropies, that offer profound insights into the early universe and the processes that shaped it. During inflation, tiny quantum fluctuations in the fabric of space-time would have been rapidly expanded to macroscopic scales. These fluctuations led to variations in the density of matter in the early universe. Over billions of years, regions of slightly higher density acted as seeds around which gas coalesced and eventually formed galaxies and clusters of galaxies. The variations in the CMB reflect these initial density variations. In essence, the CMB provides a snapshot of the universe when it was just about 380,000 years old, capturing the imprints of these primordial fluctuations. The detailed measurements of the CMB anisotropies by satellites such as WMAP and Planck have shown that the pattern of fluctuations precisely fits the predictions made by inflationary models. For instance, the scale invariant spectrum of fluctuations, a hallmark prediction of inflation, has been confirmed through observations. This scale invariance means that the distribution of fluctuations follows a specific pattern across different scales, supporting the view that they originated from quantum fluctuations magnified by cosmic inflation. Furthermore, the angular scale of the first peak in the CMB power spectrum provides evidence for a flat universe, another prediction of inflationary theory. The degree of uniformity and the specific details of the variations in the CMB thus offer strong supporting evidence for the theory of cosmic inflation, validating its predictions about the early dynamics of the universe and the mechanisms that led to the large-scale structure we observe today. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to electromagnetic radiation and consequently extremely difficult to detect directly with telescopes. Despite its elusive nature, dark matter is believed to constitute about 85% of the total matter in the universe. Its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. In the universe's early moments, dark matter played a crucial role in shaping its structure and evolution. Following the Big Bang, the universe was a hot, dense plasma of photons, electrons, and protons. However, this plasma was not perfectly uniform. It contained minute fluctuations in density. Dark matter, being unaffected by electromagnetic forces and interacting primarily through gravity, began to clump together in these regions of slightly higher density shortly after the Big Bang. These clumps of dark matter created gravitational wells that attracted ordinary, baryonic matter, facilitating the formation of the universe's first structures. As the universe expanded and cooled, these regions of dark matter and baryonic matter combined to form the seeds around which galaxies and galaxy clusters eventually coalesced. Without the gravitational scaffolding provided by dark matter, the gas would not have been able to come together and form stars and galaxies as quickly as it did. Thus, dark matter was instrumental in breaking the cosmic symmetry and creating the conditions necessary for the formation of large-scale structures in the universe. Furthermore, the distribution and movement of galaxies and galaxy clusters in the universe show patterns and velocities that cannot be explained solely by the gravitational pull of visible matter. These cosmic behaviors provide indirect evidence for dark matter's significant influence on the universe's dynamics from its earliest moments to the present day. Dark energy is a mysterious force that permeates all of space and exerts a negative pressure, leading to the accelerated expansion of the universe. Unlike dark matter, which clusters and helps to hold galaxies together through its gravitational attraction, dark energy appears to have the opposite effect. It pushes them apart. Making up about 70% of the total energy content of the universe, dark energy dominates the cosmos, yet its true nature remains one of the most profound puzzles in modern astrophysics. The influence of dark energy on the universe's expansion was first discovered in the late 1990s through observations of distant supernovae. These observations revealed that not only is the universe expanding, but the rate of its expansion is also increasing over time. This was a surprising and revolutionary finding because it had been previously assumed that the universe's expansion would be slowing down due to the gravitational pull of matter. Dark energy affects the universe's expansion through its unique property of having a negative pressure. According to Einstein's theory of general relativity, pressure contributes to the gravitational potential in the same way that mass and energy do. While the gravitational attraction of matter tries to slow down the expansion of the universe, dark energy does the opposite by accelerating it. This acceleration is uniformly distributed and affects all parts of the universe equally, influencing the fate of the cosmos by playing a crucial role in its long-term evolution. The exact nature of dark energy is still unknown, with theories ranging from a cosmological constant, a form of energy inherent to the fabric of space, to various fields and particles proposed by physics beyond the Standard Model. Understanding dark energy and its role in cosmic expansion remains one of the most compelling objectives in the quest to comprehend the universe's past, present, and future. In traditional physics, nothing might have been simply conceptualized as empty space, an absolute void devoid of matter, energy, or radiation. However, the advent of quantum field theory and our deeper understanding of the quantum vacuum has fundamentally redefined this concept in cosmological terms. Rather than an inert void, the quantum vacuum is teeming with activity. It is a dynamic state from which virtual particles constantly flicker in and out of existence due to quantum fluctuations. These particles are not directly observable in the way real particles are, but their indirect effects, such as the Casimir effect, confirm their transient presence. In the context of cosmology, this redefinition of nothing as a quantum vacuum filled with energy and potentiality has profound implications, especially when considering the origins and the fate of the universe. For example, one of the most thrilling hypotheses is that the entire universe could have sprung from a quantum fluctuation in the primordial vacuum, with inflation rapidly amplifying this minute region into the vast cosmos we observe today. This challenges not only our concept of nothing, but also our understanding of creation and existence itself. Moreover, the properties of the quantum vacuum could play a role in the fate of the universe. For instance, the energy associated with the quantum vacuum might be linked to the mysterious dark energy driving the accelerated expansion of the universe. In cosmological terms, nothing is no longer empty, but instead a bubbling brew of potentiality that underpins the very fabric of reality, challenging our perceptions and inviting us to rethink the fundamental nature of existence. Dark matter and dark energy together form the crux of a cosmic conundrum that significantly challenges our understanding of the universe's origins and its fundamental nature. While these two components make up around 95% of the total mass-energy content of the universe, their properties and behaviors starkly contrast with the baryonic or normal matter that constitutes the remaining 5%, the stars, planets, and galaxies that are familiar to us. Dark matter, with its invisible yet gravitationally influential presence, challenges our understanding because it does not interact with electromagnetic forces, meaning it cannot be observed directly through traditional means. Its existence is inferred through its gravitational effects on visible matter and the cosmic microwave background radiation. The necessity for dark matter in our cosmological models implies that our understanding of gravity and the universe's structure is incomplete without acknowledging this unseen mass. On the other hand, dark energy presents an even more profound mystery by driving the accelerated expansion of the universe, counteracting the gravitational pull that one would expect to slow this expansion down. The concept of a force or energy that works opposite to gravity challenges the very foundations laid down by Einstein's theory of general relativity. Moreover, the origin and nature of dark energy remain deeply mysterious, raising fundamental questions about the vacuum of space, quantum fields, and the fate of the cosmos. Together, dark matter and dark energy not only add to the complexity of the universe's composition, but also introduce profound puzzles regarding its origins. They necessitate a re-evaluation of our traditional theories of cosmology and physics, pushing the boundaries of our knowledge and challenging us to develop new models that can more accurately describe the universe's inception, evolution, and ultimate destiny. In essence, these mysterious components demand that we broaden our understanding far beyond the visible, into the shadowy realms that govern the structure and destiny of the cosmos itself. Neutrinos, often termed ghost particles due to their elusive nature, play an intriguing role in enhancing our understanding of the early universe. These nearly massless particles interact with matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. However, despite their elusive characteristics, neutrinos carry pivotal information about the universe's infancy and its subsequent evolution. In the first few seconds following the Big Bang, the universe was a hot, dense soup of particles, including neutrinos. These neutrinos decoupled from the rest of the matter in the universe when it was merely 1 second old, traveling virtually unimpeded ever since. Because they interact so weakly with matter, these primordial neutrinos carry with them a snapshot of the universe at that early moment, escaping the processes that later led to the formation of atoms, stars, and galaxies. By studying neutrinos, scientists can, therefore, glean insights into the conditions and processes at play in the universe's nascent stages. Furthermore, the discovery that neutrinos have mass, however minuscule, has profound implications for cosmology. It suggests that neutrinos contribute to the total mass of the universe and therefore to its overall gravitational dynamics. This has implications for our understanding of the universe's large-scale structure and the distribution of galaxies within it. Neutrinos could influence the formation of cosmic structures, and by studying their properties, scientists can refine models of cosmic evolution. In summary, neutrinos offer a unique window into the early universe, providing clues to the primordial processes that govern the cosmos's evolution. As elusive as they are, their study can inform our understanding of fundamental cosmic events, the universe's composition, and the forces shaping its expansion and structure. Their role underscores the interconnectedness of particle physics and cosmology in unraveling the mysteries of the universe. Particle accelerators, such as the Large Hadron Collider, LHC, simulate conditions of the early universe by recreating the high-energy environments that existed shortly after the Big Bang. These sophisticated machines accelerate particles, typically protons or lead ions, to near the speed of light before smashing them together in controlled collisions. These collisions generate temperatures and energy densities not naturally found on Earth, mirroring the extreme conditions that prevailed in the universe's first moments. In these fleeting microcosmic fireballs, energies reach levels where the fundamental forces of nature begin to unify, and particles that are usually stable in our current low-energy universe can spontaneously appear and decay. This high-energy environment makes possible the creation of exotic particles and states of matter, such as the quark-gluon plasma, believed to have filled the universe less than a trillionth of a second after the Big Bang. This plasma is thought to be a state of matter where quarks and gluons, normally confined within protons and neutrons, are liberated to move freely. Studying the behavior of particles under these conditions offers invaluable insights into the fundamental forces and particles that govern the universe's structure and dynamics. For instance, through particle accelerator experiments, scientists confirmed the existence of the Higgs boson, a particle that is key to understanding why other particles have mass. These experiments not only advance our knowledge of particle physics but also provide a tangible link to the conditions and processes of the early universe, helping to validate or refine theoretical models of its evolution. By simulating the early universe's conditions, particle accelerators serve as a bridge between the worlds of particle physics and cosmology, allowing scientists to explore and test theories about the universe's origin, its fundamental constituents, and the forces shaping its evolution. The discovery of gravitational waves has profound implications for cosmological theories, opening a new frontier in our understanding of the universe. Gravitational waves are ripples in the fabric of space-time, generated by some of the most violent and energetic processes in the cosmos, such as merging black holes or neutron stars. Predicted by Albert Einstein's general theory of relativity in 1916, their existence was directly confirmed a century later by the LIGO and Virgo collaborations, marking a milestone in observational astronomy and cosmology. One significant implication of gravitational waves is their potential to provide a unique insight into the very early universe. Unlike electromagnetic radiation, light, which can become scattered or absorbed, gravitational waves pass through matter almost unimpeded, carrying with them information from their source. This makes them a pristine messenger from events like the Big Bang or the inflationary period that followed, offering clues about the universe's infancy that are not accessible through other means. Gravitational waves also have implications for our understanding of fundamental physics and the nature of gravity. By studying these waves, scientists can test general relativity in regimes of extreme gravity that were previously inaccessible. This includes probing the enigmatic interiors of black holes and examining the dynamics of neutron-star collisions, which could reveal new physics beyond our current models. Furthermore, the detection of gravitational waves from the merger of binary neutron stars has already contributed to a better understanding of the origin of heavy elements in the universe, such as gold and platinum, supporting the theory that these elements are produced in neutron-rich environments. Finally, gravitational waves could help resolve existing puzzles in cosmology, such as measuring the universe's expansion rate more accurately. Since the speed and characteristics of gravitational waves are well defined, they can be used as cosmic rulers to gauge distances across space more precisely than traditional methods. In summary, the detection of gravitational waves not only confirms a central prediction of general relativity, but also provides a novel tool for probing the universe's most energetic phenomena, shedding light on the early universe, testing the limits of known physics, and refining our cosmological models. Our current cosmological models, while remarkably successful in describing the universe on the largest scales, still face significant limits and unresolved questions. One of the primary models, the lambda cold dark matter (LCDM) model, which includes dark energy L and cold dark matter, accurately predicts the large-scale structure of the universe, the cosmic microwave background radiation, and other key phenomena. However, several challenges and mysteries remain. Firstly, the nature of dark matter and dark energy constitutes the most glaring gap in our understanding. Despite accounting for about 95% of the total mass-energy content of the universe, what dark matter and dark energy are made of remains unknown. This gap limits our understanding of the universe's composition and dynamics fundamentally. Another limitation is the horizon problem, which, although the inflationary model attempts to address it, remains a subject of theoretical exploration. The inflationary model proposes a rapid expansion of the early universe to explain the uniformity of the cosmic microwave background radiation across regions that should not have been in causal contact. However, the exact mechanism and potential alternatives of this rapid inflation are still hot topics of research and debate. Moreover, discrepancies in measurements of the Hubble constant, which describes the universe's rate of expansion, suggest that our understanding of the cosmos's evolution might be incomplete. Different methods yield slightly different values, indicating potential gaps in our models or new physics yet to be discovered. Furthermore, the formation and distribution of galaxies and the smaller-scale structures of the universe aren't perfectly predicted by LCDM. Issues like the missing satellite problem, where simulations predict more small satellite galaxies around galaxies like the Milky Way than observed, hint at potential refinements needed in our understanding of dark matter and galaxy formation. Lastly, the integration of quantum mechanics with general relativity remains a fundamental challenge in physics. Our current cosmological models operate within the framework of general relativity, which does not incorporate quantum effects. A quantum gravity theory would be required to fully understand the universe's behavior at all scales, particularly during the Planck Epoch, the universe's earliest moments. In essence, while our current cosmological models have been incredibly successful in explaining a wide range of astronomical observations, they also highlight the limits of our understanding and the ongoing need for theoretical and observational advances to deepen our knowledge of the universe. Scientists estimate the age of the universe using several methods, with observations of the cosmic microwave background radiation being one of the most critical. The CMB is the afterglow radiation from the Big Bang, and its properties provide us with a snapshot of the universe when it was only about 380,000 years old. By studying the CMB's temperature fluctuations and its detailed characteristics with experiments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, scientists can infer key parameters about the universe's expansion. The lambda cold dark matter model, which includes dark energy and cold dark matter, uses these parameters to describe the evolution of the universe from the Big Bang to the current day. By running this model backwards, scientists are able to estimate the age of the universe as approximately 13.8 billion years. Another method involves studying distant objects in the universe, such as high redshift galaxies and quasars, as well as their relationship to their surroundings. The light from these objects has taken billions of years to reach us, hence observing them is like looking back in time. Their properties, such as their chemical compositions and distances, help refine models of cosmic evolution, contributing to the measuring of the universe's age. Star clusters provide a complementary method for estimating the universe's age. There are two types of star clusters: globular clusters, which are old and contain some of the most ancient stars in our galaxy, and open clusters, which are younger. By determining the ages of the oldest stars, particularly low-mass stars that have long lifespans and are found in globular clusters, astronomers can set a lower limit on the age of the universe. They use stellar evolution models to estimate how long these stars have been burning, and thus how long it has been since the Big Bang. Finally, techniques involving nuclear cosmochronology, measuring the presence of specific radioactive isotopes and their decay products in meteorites and certain stars, offer another path to understanding the universe's timeline. This method, however, provides more insight into the age of the Milky Way galaxy and its components, rather than the universe as a whole. Taken together, these methods provide a coherent picture of the universe's age, relying on the fundamental physics of light, gravity, and atomic processes, painting a compelling portrait of a universe that has been evolving over billions of years. Observations of distant galaxies play a crucial role in informing our understanding of the universe's early expansion and its overall evolution. As light travels at a finite speed, looking at distant galaxies allows astronomers to peer back in time and observe the universe as it was billions of years ago. This time-lapse view is instrumental in constructing a historical record of cosmic evolution. One of the key pieces of evidence for the universe's expansion comes from the observation of the redshift of light from distant galaxies. First observed by Edwin Hubble in the 1920s, this redshift occurs because the light from these galaxies stretches as the universe itself expands, shifting their light toward the red end of the visible spectrum. The farther away a galaxy is, the more its light has been redshifted, indicating that the universe is expanding in all directions. This observation was the cornerstone for the development of the Big Bang theory, fundamentally changing our understanding of the universe's origins and its dynamic nature. Moreover, observations of the most distant galaxies allow astronomers to measure the rate of the universe's expansion at different epochs. By comparing these rates over time, scientists have discovered that the universe is not only expanding, but that this expansion is accelerating, a discovery attributed to a mysterious force dubbed dark energy. This finding has profound implications for the fate of the universe and challenges prior understandings of cosmic dynamics. Additionally, the study of distant galaxies has uncovered populations of very young galaxies existing when the universe was just a few 100 million years old. These observations provide invaluable insights into the processes of galaxy formation and the evolution of structures in the early universe. Galaxies in their infancy show characteristics markedly different from their modern counterparts, offering clues about the conditions and predominant processes of the early cosmos. Furthermore, the distribution and clustering of distant galaxies across the sky allow cosmologists to test theories of cosmic inflation, the ultra-rapid expansion that the universe underwent a fraction of a second after the Big Bang. The patterns observed in the large-scale structure of the universe today are a direct imprint of quantum fluctuations magnified by cosmic inflation, providing a powerful tool for understanding this pivotal epoch. In summary, observations of distant galaxies serve as windows into the universe's past, offering critical insights into the early expansion of the cosmos, the nature of dark energy, the process of galaxy formation, and the mechanisms that have shaped the universe from its earliest moments to the present day. In the grand tapestry of cosmology, the Planck Epoch plays the role of the universe's opening act, a fleeting moment that occurred immediately after the Big Bang, approximately 13.8 billion years ago. This epoch spans a minuscule fraction of a second, specifically the first 10 to the negative 43rd of a second, from 0 to the blink of an eye. During this time, the universe was condensed into a point of infinite density and temperature, a state beyond our current understanding and the laws of physics as we know them. Scientists believe that during the Planck Epoch, the four fundamental forces of nature, gravitational, electromagnetic, strong nuclear, and weak nuclear, were unified into one singular force. The significance of the Planck Epoch lies in its mystery and the boundary it sets for our understanding. It represents the edge of our scientific knowledge, as beyond this point, the classical theories of physics break down, and only quantum theory of gravity, a theory yet to be fully developed, can potentially describe the events. Thus, the Planck Epoch defines the very beginning of time and the universe, a point from which everything we know, from galaxies to atoms, eventually emerged. This epoch underscores the continuous quest for a deeper understanding of the origins of our universe, pushing the boundaries of science into the unknown. As we stand on the precipice of unprecedented technological advancements, the future holds the promise of redefining our cosmological theories in ways we're only beginning to imagine. One significant frontier is the development of more sophisticated telescopes and observational instruments capable of peering further back in time and space with unprecedented clarity. This leap in observational power might unveil phenomena or objects that challenge our current understanding of the universe's formation and evolution, forcing us to revise or even discard established theories. Moreover, advances in quantum computing could revolutionize our ability to process astronomical data, uncovering patterns and insights within the cosmic background radiation or the distribution of galaxies across the cosmos that were previously obscured. This, in turn, could provide empirical evidence supporting or refuting theoretical models of the universe's structure and origin, such as inflation theory or the nature of dark matter and dark energy. Perhaps most tantalizing is the potential development of a unified theory of physics that reconciles general relativity and quantum mechanics. Such a theoretical breakthrough could fundamentally alter our understanding of gravity, space-time, and the conditions of the early universe, possibly providing clear insights into the enigmatic Planck Epoch. Armed with this comprehensive framework, cosmologists might be able to simulate the birth and evolution of the universe with unparalleled accuracy, offering unprecedented insight into our cosmic origins. Primordial black holes are a theoretical type of black hole that is proposed to have formed soon after the Big Bang, during the first moments of the universe's existence. Unlike stellar black holes, which are formed by the collapse of massive stars, primordial black holes are thought to have originated from the high-density fluctuations in the incredibly hot and dense early universe. These fluctuations could cause certain regions of space to collapse under their own gravity, leading to the creation of black holes in the moments following the universe's birth. If primordial black holes exist, they could provide a unique window into the conditions of the early universe, offering clues about the nature and properties of dark matter, the distribution of matter in the universe, and the behavior of space and time under extreme conditions. The existence of primordial black holes could potentially solve some of the mysteries surrounding dark matter. If these black holes account for a significant portion of the universe's dark matter, their distribution and mass could help scientists better understand how galaxies formed and evolved. Additionally, observing how primordial black holes interact with their surroundings and with each other could provide empirical data on the nature of gravity and the dynamics of space-time, testing the limits of Einstein's theory of general relativity. The intriguing concept of dark flow refers to the observed large-scale motion of galaxy clusters, which appears to be uniformly streaming across the vast expanses of the universe, moving in a specific direction. This phenomenon, discovered through observations of the cosmic microwave background radiation and the movement of galaxy clusters, challenges our understanding of how the universe behaves on its grandest scales. Dark flow hints at forces or structures beyond the observable universe influencing the motion of matter, which could have profound implications for theories of the universe's origins. One potential implication of dark flow is its alignment with theories proposing the existence of a multiverse, where our universe is just one of many, each with its own laws of physics. Dark flow could be evidence of gravitational forces emanating from other universes, pulling matter within our own universe in a specific direction. This notion challenges the traditional cosmological principle, which posits that the universe is homogeneous and isotropic on large scales, suggesting instead that the universe might have a preferred direction influenced by external universes. Dark flow could provide insights into the period of cosmic inflation, an extremely rapid expansion of the universe thought to have occurred fractions of a second after the Big Bang. If the initial conditions of inflation were not uniform, this could have led to variations in the distribution of matter and energy that manifest today as dark flow. Such an understanding could refine our models of inflation, offering a more nuanced picture of the universe's explosive beginnings. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, has become a pivotal tool in cosmology, offering a unique method to observe the otherwise invisible fabric of the universe. When light from distant galaxies passes near massive objects, such as other galaxies or clusters, the gravitational field of the intervening mass warps spacetime, bending the path of the light. This results in magnified, distorted, or multiplied images of the distant galaxies, providing critical insights into the nature of the intervening mass and the geometry of the universe. Cosmological findings from gravitational lensing are seamlessly integrated into our theoretical frameworks, enriching our understanding of several key aspects of the universe. Firstly, gravitational lensing has become instrumental in mapping the distribution of dark matter. As dark matter does not emit, absorb, or reflect light, it remains invisible to traditional telescopic observations. However, by studying the light distorted by gravitational lensing, astronomers can infer the presence and distribution of dark matter, thus filling in a critical piece of the cosmic puzzle regarding its elusive nature. Furthermore, gravitational lensing has critical implications for our knowledge of the universe's overall structure and expansion. By observing how light bends around massive clusters, scientists can measure the universe's rate of expansion and gain insights into the influence of dark energy, a mysterious force speeding up the expansion of the universe. These measurements, in turn, help refine the parameters of the lambda cold dark matter model, the prevailing theoretical framework that describes the cosmos's origin, content, and evolution. Additionally, gravitational lensing has facilitated the detection of extremely distant and faint galaxies, allowing astronomers to peer back into the early epochs of the universe. This window into the distant past aids in understanding how galaxies form and evolve over cosmic time, further integrating gravitational lensing findings into broader theories concerning structure formation in the universe. Theoretical physicists model the universe's origin by weaving together the fabric of mathematics, observation, and imaginative speculation into a cohesive framework that attempts to explain the cosmos's earliest moments. At the heart of these efforts lies the Big Bang theory, the leading explanation for the universe's origin, positing that the universe began as an incredibly hot and dense point approximately 13.8 billion years ago and has been expanding ever since. To model these initial conditions and the subsequent evolution of the universe, physicists rely on a set of equations derived from the general theory of relativity coupled with quantum mechanics, though the latter's full integration remains one of physics' greatest challenges. Cosmic inflation, another critical piece of the theoretical puzzle, proposes that the universe underwent a rapid expansion within the first fraction of a second after the Big Bang. This theory helps to explain several observational puzzles, such as the universe's large-scale uniformity and the origin of the tiny fluctuations that eventually led to the formation of galaxies. Inflationary models are tested by examining the cosmic microwave background radiation, the afterglow of the Big Bang, using precise satellite observations that measure this radiation's temperature fluctuations across the sky. Moreover, to understand the universe's composition and its subsequent evolution, theoretical physicists delve into the mysteries of dark matter and dark energy, two entities that constitute about 95% of the universe's total mass energy content but remain poorly understood. Through simulations and mathematical models, researchers explore how these enigmatic components influence the universe's structure and expansion rate, comparing their models against astronomical observations. String theory and loop quantum gravity represent two speculative yet promising approaches to unifying gravity with the other fundamental forces, potentially offering insights into the pre-Big Bang universe. These theories attempt to describe the universe at its most fundamental level, incorporating the principles of quantum mechanics into the fabric of space-time itself. Loop quantum gravity stands as a groundbreaking endeavor, striving to merge the principles of quantum mechanics with general relativity, thereby providing a coherent quantum theory of gravity. String theory, with its revolutionary concepts of branes and extra dimensions, offers a profound challenge to our conventional understanding of nothing, or the vacuum of space. At its core, string theory posits that the fundamental components of the universe are not zero-dimensional point particles, but rather one-dimensional strings that vibrate at different frequencies to manifest as the particles we observe. The inclusion of higher-dimensional objects, known as branes, short for membranes, adds layers of complexity to this framework. Branes can possess various dimensions, with our familiar three-dimensional universe potentially being one such brane embedded in a higher dimensional space. This reimagining of the universe's fundamental structure dramatically shifts our perception of the vacuum. In classical physics and general relativity, nothing, or the vacuum, is viewed as empty space, devoid of matter or energy. However, string theory reveals that this supposedly empty space is a seething cauldron of vibrating strings and branes, buzzing with quantum fluctuations and governed by the hidden dimensions these objects inhabit. What appears as nothing to our senses and instruments is, in string theory, a complex tapestry of interactions and potentialities that underlie the fabric of reality. The concept of branes further suggests that our universe, our entire observable reality, may be confined to just one brane, floating in a higher dimensional space that contains other branes, each potentially hosting its own universe with its own laws of physics. This opens up the radical possibility that interactions with other brains could have consequential effects on our universe, influencing the fundamental constants and the very nature of our cosmos. For instance, the collision of our universe's brain with another could conceive phenomena that challenge our traditional understanding of the cosmos's origins, possibly providing alternative explanations to the Big Bang itself. String theory's redefinition of nothing has implications for understanding the vacuum's role in the universe's birth and evolution. Quantum fluctuations in the vacuum, a sea of potential brains and strings, could have been the spark that initiated the Big Bang, suggesting that the universe's creation might not require a cause outside of nothing, but that nothing itself possesses the seeds of universes yet unborn. The multiverse theory is a provocative and expansive concept in modern physics and cosmology that suggests our universe is but one of an enormous number, perhaps an infinite number, of universes that collectively constitute the multiverse. Each universe within the multiverse could have vastly different physical laws, constants, and overall characteristics. This theory emerges, in part, from the attempts to reconcile the principles of quantum mechanics with the theory of general relativity, and it finds support in the frameworks of inflationary cosmology and string theory. One of the most intriguing aspects of the multiverse theory is its potential explanation of how our universe, and indeed other universes, could have originated from nothing. In the context of the multiverse, nothing does not imply a void or absence of existence. Rather, it refers to a quantum vacuum state that possesses a bubbling sea of virtual particles and energy fluctuations due to the principles of quantum mechanics. Inflationary cosmology, a key pillar supporting the multiverse, posits that our early universe experienced a rapid exponential expansion driven by a high-energy vacuum state. This initial inflationary period could potentially spawn not just our universe, but an infinite number of bubble universes, each emerging from its own patch of the inflating space-time fabric. Such a mechanism suggests that our universe could have budded off from the quantum foam of the greater multiverse, essentially coming into existence from quantum fluctuations in the nothingness of the pre-existing space-time fabric. Moreover, string theory introduces the idea of a landscape of possible vacuum states, each corresponding to different configurations of string vibrations and brane arrangements. Transitions between these vacuums could catalyze the birth of new universes. Again, this hints at the possibility of universes springing into existence from the quantum vacuum, essentially nothing by classical definitions, yet teeming with latent potential in the quantum realm. The notion that our universe could originate from nothing challenges and expands our conventional understanding of causality and existence. It implies that the laws of physics allow for the spontaneous creation of universes given the right conditions in the quantum vacuum. This profound implication not only influences how we perceive our universe's origins, but also how we conceptualize the broader cosmos's structure and the very nature of reality itself within the speculative yet fascinating framework of the multiverse theory. The philosophical implications of a universe that originated from nothing touch on some of the most profound questions regarding existence, creation, and the nature of reality itself. In a traditional sense, nothing suggests an absence, a void devoid of properties or potential. However, modern physics, particularly theories that entertain a universe emerging from nothing, such as quantum fluctuations within a vacuum, redefine nothing as a state brimming with latent possibilities. This redefinition challenges and enriches philosophical discourse in several ways. Firstly, it prompts a re-evaluation of causality. The classical notion that every effect must have a cause is put to the test if the universe can spontaneously emerge from a vacuum state without a preceding cause. This raises questions about the sufficiency of causal explanations for the universe's existence and opens discussions on whether our universe requires a cause outside of naturalistic explanations. Additionally, the idea of a universe originating from nothing intersects with questions about why there is something rather than nothing, a central concern in metaphysics. It suggests that the natural state of nothingness can inherently possess the potential for becoming something, which implies that existence might be a more natural condition of reality than previously thought. This perspective could shift philosophical inquiry towards exploring how existence arises from non-existence within the frameworks of quantum mechanics and cosmology. The concept challenges traditional metaphysical and theological arguments about the creation of the universe and the need for a creator. If the universe can indeed originate from nothing by natural processes, this could lead to a re-evaluation of arguments for the existence of a divine creator, prompting dialogues between science, philosophy, and theology about the origins of existence and the laws governing reality. The notion of a universe emerging from nothing also invites deeper exploration into the nature of nothingness itself. Philosophers might probe whether nothing can truly exist, or if nothingness, as conceived by quantum theory, implies that the vacuum is a rich tapestry of potential states and energies, thus redefining our understanding of non-existence. The possibility of undiscovered principles of physics that could explain the universe's origin from nothing is not only enticing, but also a driving force behind ongoing research in theoretical physics and cosmology. The history of science is replete with instances where anomalies in observed phenomena led to the development of new theories that radically transformed our understanding of the universe. As such, the current frameworks we use to describe the cosmos, general relativity and quantum mechanics, though profoundly successful, also hint at their own limitations, especially when it comes to understanding the universe's very beginning. The concept of the universe originating from nothing nudges us toward the boundaries of these established theories. General relativity breaks down at the singularity point of the Big Bang, where densities and temperatures become infinitely high, and quantum mechanics introduces a realm where particles can indeed emerge from the vacuum due to fluctuations in energy. These hints suggest that our current understanding of nothing might be an incomplete picture, necessitating new physics to fully comprehend how the universe could arise from such a state. One promising area of research is the unification of quantum mechanics and general relativity into a theory of quantum gravity. Theories like loop quantum gravity and string theory attempt to describe the fabric of spacetime at the Planck scale, where the effects of both quantum mechanics and gravity converge. These or other yet undiscovered frameworks might reveal mechanisms by which nothing, a quantum vacuum with its fluctuations, could give birth to a universe, providing a natural explanation for its origin. Moreover, the exploration of dark energy and dark matter, which constitute most of the universe's mass-energy content yet remain largely mysterious, could unveil new physics that plays a crucial role in the universe's birth and evolution. Discoveries in these areas could radically alter our understanding of the cosmos and its origins. Advancements in observational technology and techniques might allow us to detect signals from the universe's earliest moments, providing empirical clues that challenge existing theories and guide the development of new ones. For example, observations of the cosmic microwave background radiation have already revolutionized cosmology, and future observations could contain signatures of pre-Big Bang physics. Manipulating fundamental cosmological forces, an idea that presently sits firmly within the realm of theoretical physics and speculative science writing, opens a Pandora's box of ethical considerations. These considerations stem from the profound implications such manipulations could have on the universe's structure, the fabric of space-time, and the very laws that govern cosmic evolution. While the practicality of manipulating forces like gravity or electromagnetism on a cosmological scale is far beyond our current technological capabilities, the theoretical contemplation of such possibilities invites ethical scrutiny. Firstly, there's the concern of unintended consequences. Manipulating fundamental forces could potentially destabilize cosmic structures, disrupt the trajectory of celestial bodies, or even alter the conditions necessary for life as we know it. The scale and permanence of these consequences necessitate a careful consideration of the risks involved, analogous to ethical debates in other fields like genetic engineering or artificial intelligence, where the potential for irreversible harm exists. The question of consent arises when considering large-scale interventions in cosmological phenomena. Who has the right to make decisions that could affect the entire universe, potentially impacting untold numbers of civilizations or life forms? This raises issues of cosmic stewardship and intergenerational ethics, where the needs and rights of future beings, human or otherwise, must be weighed against present desires to explore or modify the cosmos. The manipulation of cosmological forces could exacerbate existing inequalities or give rise to new forms of disparity. If such capabilities were to become feasible, who would control them? The concentration of such power could lead to dominance over cosmic resources or territories, invoking the need for frameworks of cosmic justice and governance that ensure equitable access and prevent exploitation. Ethical considerations must also address the preservation of the natural cosmic heritage. Just as we value natural landscapes on Earth and seek to preserve them from undue human alteration, so too might we come to view the universe's wonders as entities worthy of preservation in their own right, meriting protection from human meddling. Engaging with these ethical considerations prompts deeper philosophical reflections on humanity's place within the cosmos and our relationship with the universe at large. It challenges us to consider the limits of human ambition and the responsibilities that come with advanced technological and scientific capabilities. Pre-Big Bang scenarios delve into the enigmatic realm of what might have existed or occurred before the universe's explosive moment of creation, as traditionally understood. These speculative yet theoretically rich ideas aim to address the limitations and open questions left by the Big Bang theory, particularly regarding what ignited the Big Bang and whether the universe could have had a history prior to that point. A few leading concepts have emerged in the scientific discourse, challenging and expanding our understanding of the universe's origins. One prominent theory is the idea of a cyclic or oscillating universe, which proposes that the universe undergoes an infinite series of expansions and contractions. According to this model, the Big Bang is just the latest in a series of cosmic cycles. A previous universe contracted to a highly dense state, possibly a singularity, before bouncing back and expanding into the universe we observe today. This cycle of big crunches followed by big bangs suggests a timeless, eternal process, devoid of a singular beginning. Another intriguing pre-Big Bang theory is that of the ikpyrotic universe, inspired by string theory concepts. This scenario suggests that our universe's Big Bang originated from the collision of two or more higher dimensional branes. These branes, existing within a higher dimensional space, move and eventually collide, channeling energy into the creation of a new universe. This model not only provides a potential mechanism for the Big Bang, but also suggests a way to unify the forces of nature through the frameworks of string theory and M theory. Quantum cosmology presents another approach, where the rules of quantum mechanics are applied to the universe as a whole. In these models, the singularity at the Big Bang may be replaced by a quantum bounce, a concept where quantum effects prevent the singularity and instead cause the universe to contract and then bounce back before reaching an infinite density. These theories often utilize frameworks like loop quantum gravity to conceptualize how space, time, and matter behave under extreme quantum conditions at the universe's inception. These pre-Big Bang scenarios share a common goal: to extend our understanding of the universe's origins beyond the limits of classical Big Bang cosmology, incorporating insights from quantum mechanics, string theory, and other advanced theoretical frameworks. By doing so, they not only offer possible explanations for the conditions leading up to the Big Bang, but also invite reconsideration of fundamental questions about time, existence, and the ultimate nature of the cosmos. Although highly speculative and facing significant technical and observational challenges, these theories underscore the dynamic and ever-evolving nature of cosmological inquiry, driving forward our quest to comprehend the universe's deepest mysteries. The concept of eternal inflation introduces a profound and radical reshaping of our understanding of the universe's origins, propelling the discussion into realms that challenge the very notion of a singular, isolated universe birthed from a conventional Big Bang event. At the heart of eternal inflation is the idea that the rapid expansion described by the inflationary theory, wherein the nascent universe underwent an exponential increase in size over a minuscule fraction of a second, never completely ceases but continues eternally in various regions of space. According to this scenario, the universe can be likened to an ever-expanding cosmic bubble bath, with each bubble representing a separate universe within a vast, possibly infinite, multiverse. Within this framework, what we perceive as our universe is merely one bubble in a colossal froth, with inflation ceasing in our local region while it perpetuates without end in others. This picture challenges traditional cosmological models by proposing that the Big Bang was not the singular origin of all there is, but one event among countless others, with each bubble universe potentially governed by its own set of physical laws and constants. Eternal inflation raises profound implications for understanding the universe's origins and its ultimate fate. First, it dilutes the concept of a beginning of time and space as we know it, suggesting instead a timeless, ever-inflating multiverse that continually spawns new universes. This shift pushes the boundaries of the Big Bang theory and invites a revaluation of the initial conditions that led to our universe's birth, suggesting they might be but one possibility among an infinite range of scenarios played out across the multiverse. Secondly, the concept of eternal inflation broadens the cosmological horizon beyond the observable universe to include the possibility of an infinite number of unobservable universes, each potentially hosting vastly different forms of matter, energy, and even varying constants of nature. This non-uniformity puts into perspective the fine-tuning observed in our universe's physical laws, suggesting they may be the result of random processes on a cosmic scale rather than requiring finely adjusted initial conditions or new physics to explain. Furthermore, eternal inflation intersects with and is bolstered by developments in string theory, particularly the idea of a landscape of possible vacuum states, each leading to the creation of different universes with unique properties. This confluence of ideas from inflationary cosmology and string theory underscores the theoretical possibility of a multiverse, further pushing the envelope on our understanding of the cosmos's origins. Theories of quantum gravity, which aim to reconcile the seemingly irreconcilable frameworks of quantum mechanics and general relativity, carry profound implications for our traditional concepts of the universe's beginning. At the core of these implications is the potential to fundamentally alter our understanding of the conditions, nature, and even the necessity of a singular initial event, traditionally conceived as the Big Bang. One of the most striking implications is the potential elimination of the singularity at the universe's beginning, an infinitely dense, hot, and small point where the laws of physics as we know them cease to function. Quantum gravity suggests that the universe could have a finite size at its earliest moment, governed by quantum laws that prevent the formation of a singularity. This would mean that the universe did not emerge from nothing, but always had a quantifiable, albeit exceedingly small, essence. Furthermore, theories of quantum gravity, such as loop quantum cosmology, offer a model where Big Bang singularities are replaced by Big Bounce scenarios. In these models, the universe's contraction under gravity could reach a critical point where quantum effects generate a repulsive force, causing a bounce and initiating an expansion phase. This suggests that our universe could be the latest cycle in an eternal sequence of collapses and expansions, countering the traditional view of a universe with a definite beginning. Additionally, quantum gravity can introduce a context where time itself emerges from a primordial state governed by quantum laws. This challenges the very foundation of traditional cosmological models where time, and thus causality and sequence, pre-exist the universe. In a quantum gravity framework, time and space may be emergent properties, suggesting the Big Bang wasn't the beginning of time, but a transition phase in a timeless quantum realm. Moreover, the integration of quantum phenomena and gravity hints at the possibility of multiple or parallel universes, as suggested by both quantum mechanics and inflation theory. Quantum gravity could provide the theoretical framework necessary for the existence of these universes to be not just speculative, but an intrinsic aspect of the cosmos's fundamental structure. This radically broadens the scope of what we consider the universe, challenging the notion of a unique, isolated cosmic history. Delving into the enigmatic world of particle physics might soon offer us unprecedented insights into the very origins of the universe. One of the most compelling areas of exploration lies in the study of the Higgs boson, a particle once theorized and then discovered, which has fundamentally changed our understanding of mass. Researchers are now pondering what else might be lurking in the subatomic landscape that could unlock the next chapter in our cosmic story. There's talk, for instance, of a hypothetical particle called the graviton, which, if discovered, could illuminate the mystery of gravity's place in the quantum realm. Such a breakthrough would not just rewrite the textbooks on particle physics, but might also offer a new lens through which to view the universe's birth. Imagine uncovering evidence of multidimensional space or finding the first tangible proof of other universes within a multiverse. This isn't just speculation. With the advancements in particle accelerators and detection technologies, the stage is set for a possible revolution in our understanding of the early universe. Older audiences who have witnessed the transformation of cosmology from speculative to a precision science may find these potential discoveries particularly fascinating, offering a fresh perspective on the cosmos that has intrigued humanity for centuries. Advanced cosmological theories, from the concept of a multiverse to the intricacies of dark matter and dark energy, extend far beyond the realm of science, deeply probing into the domain of philosophy and existential contemplation. These theories often challenge our very understanding of existence, prompting us to question not only the nature of our universe, but our place within it. For instance, the multiverse theory, which suggests the existence of numerous, perhaps infinite, universes beyond our own, raises the profound question of determinism versus randomness. If countless universes exist, each with its own set of physical laws, where does that leave the notion of destiny? Are our lives merely one possibility in an endless sea of outcomes? Furthermore, the elusive essence of dark matter and dark energy, which together constitute around 95% of the total mass energy content of the universe, confronts us with the unsettling realization of how little we know about the cosmos we inhabit. This humbling acknowledgement paves the way for existential reflection on the significance of human life and consciousness in a largely unknown and possibly indifferent universe. Such contemplations remind us that the pursuit of cosmological understanding stretches far beyond the acquisition of knowledge, touching the core of our existence and our relentless quest for meaning amidst the vast unknown. The possibility of a cyclic universe, one that expands and then contracts in an eternal series of big bangs and big crunches, introduces a profoundly different perspective on the nature of cosmological origins. This theory challenges the traditional view of the universe having a singular beginning and suggests instead that the universe undergoes infinite cycles of birth, life, and rebirth. This cyclic model fundamentally alters our narrative of time and existence, implying that our universe might be just one chapter in an endless cosmic story. It propels us to reconsider the concept of a beginning itself. Is it merely a point in an infinite loop, devoid of the singularity that traditional Big Bang cosmology proposes? Additionally, this perspective influences the philosophical discourse on causality, the arrow of time, and the nature of cosmic evolution. If the universe is eternal and cyclical, then the origins of matter, energy, and the laws governing them may need to be understood not as singular events, but as processes repeated infinitely throughout cosmic history. For researchers and scholars, this poses a unique challenge in reconciling the observable universe with a model that defies the conventional understanding of time and genesis. For the more philosophically inclined, it presents an opportunity to ponder the very notion of beginnings and endings, urging a reconceptualization of our place and purpose within a potentially eternal and cyclic cosmos. The application of non-linear time concepts to the universe's origins introduces a fascinating twist to traditional cosmology, challenging the linear progression from the Big Bang to the present universe. In a non-linear time framework, the past, present, and future do not follow in a straight line, but could potentially intersect or even run parallel to each other. This implies that the origins of the universe could be influenced by events from its future, blurring the distinction between cause and effect, a concept unthinkable in classical physics but conceivable in the realm of quantum mechanics and general relativity. Such a reimagining could potentially solve some of the deepest cosmological mysteries, such as how conditions were just right for the universe to begin and evolve. It might suggest that the fine-tuning of the universe for life is no coincidence, but rather a result of the universe's laws shaping themselves over the cosmic timeline. This perspective radically alters our understanding not just of the universe's origins, but of time itself, positing that the very fabric of the cosmos is weaved with a temporal complexity beyond human comprehension. For those intrigued by the philosophical implications, it opens up a plethora of questions regarding destiny, free will, and the nature of reality. Is our future already written in the stars, or are we the architects of cosmic destiny? The intersection of non-linear time and cosmology not only expands the boundaries of scientific inquiry, but also offers a profound narrative on the interconnectivity of existence. The pursuit to fully understand the universe's origins is one of humanity's most ambitious endeavors, weaving together the threads of science, philosophy, and sheer curiosity. While remarkable strides have been made in cosmology, suggesting we may inch closer to unraveling the mysteries of the universe's beginnings, it's conceivable that some aspects will forever elude our grasp. The fundamental nature of scientific inquiry, bound by the limits of observation and the constraints of human cognition, implies that our understanding is perpetually evolving, navigated by the tools and theories at our disposal. As we delve deeper into the fabric of the cosmos, new layers of complexity emerge, each discovery propelling us towards further questions. For instance, the enigmatic dark matter and dark energy, constituting the vast majority of the universe, yet remaining largely invisible, hint at the profound unknowns still before us. Moreover, the speculative realms of string theory and the multiverse introduce concepts that may forever skirt the periphery of empirical validation, residing in the domain of theoretical possibility. This ongoing dance with the cosmos, where each step forward reveals new horizons of mystery, emphasizes the beauty of exploration itself, transcending the mere quest for answers. The universe's origins, intertwined with questions of existence and purpose, may always hold elements of mystery, serving as a humbling reminder of our place within the vast cosmic tapestry and fueling the relentless human drive to understand the unknowable. The discovery of other universes, a concept that stretches the fabric of our current understanding and imagination, poses profound implications for our conception of nothing. Traditionally, Nothing has been thought of as a void, an absence of matter, energy, space, and time, a concept already challenging to reconcile with the quantum world, where particles pop in and out of existence from seemingly nowhere. The idea that our universe could be one of many within a vast multiverse further complicates this notion, suggesting that nothing might actually be teeming with the potential for universes. It pushes the boundaries of our understanding from viewing nothing as an empty stage to conceiving it as a cosmic seedbed from which universes can emerge. This shift not only redefines our conceptual grasp of nothing, but also forces us to rethink the foundational principles that govern our universe and its origins. If other universes exist, each with possibly different laws of physics, nothing may be subject to forces or laws completely unknown to us, acting as a sort of cosmic chrysalis. Moreover, in a multiverse scenario, the conditions that lead to the birth of universes could be commonplace, and nothing might be a state brimming with the latent energy and potential for creation. This profound reimagining underscores the limits of human cognition in grasping the true nature of reality and existence, inviting an existential exploration into the very essence of creation and the fabric of the cosmos. Anomalies in cosmological data serve as the intriguing puzzles that challenge the bedrock of existing theories, compelling the scientific community to reassess fundamental understandings of the universe's mechanics. When observations deviate from what the prevailing models predict, these discrepancies become catalysts for innovation and revision in the cosmic narrative. For instance, the unexpected acceleration in the universe's expansion rate, highlighted by observations of distant supernovae, clashed with the then-current models, leading to the revolutionary concept of dark energy. Similarly, discrepancies in the cosmic microwave background radiation, the afterglow of the Big Bang, have raised questions about the uniformity and structure of the universe that the standard model of cosmology struggles to fully address. These anomalies act as beacons, signaling the gaps in our comprehension and often hinting at new physics or unseen aspects of the cosmos. They challenge the status quo, pushing scientists to explore beyond conventional boundaries, whether through refining existing theories or formulating entirely new paradigms. This relentless pursuit driven by anomalies not only enriches our understanding of the universe, but underscores the evolving nature of scientific inquiry, where every question answered leads to deeper, more complex questions, painting an ever-expanding picture of the cosmos that is far stranger and more wonderful than currently understood. Chaos theory, with its focus on the sensitivity of systems to their initial conditions and the complex, unpredictable outcomes that can result, has a profound and intriguing role in cosmology and our understanding of the universe's beginnings. This mathematical framework sheds light on how the intricate structures and patterns observed in the cosmos, from the distribution of galaxies to the formation of solar systems, might arise from seemingly simple, chaotic states. In the nascent moments following the Big Bang, the universe was an extremely hot, dense point of energy and matter. Chaos theory suggests that even minute variations in this early state, no matter how small, could have drastic effects on the development of the universe. This principle, often encapsulated by the metaphor of a butterfly's wings causing a tornado, might explain the large-scale structures observed today and provides a potential pathway from the uniformity predicted by the Big Bang to the clumpy, structured universe we observe. Chaos theory offers a perspective on the fundamental unpredictability embedded within the cosmos's evolution. It underscores that the universe's long-term behavior might be inherently unpredictable due to the complex interplay of forces and reactions that have been unfolding since its inception. This has implications for understanding everything from the formation of galaxies to the eventual fate of the universe, challenging cosmologists to consider the limits of predictability in a system as dynamic and complex as the universe. In bridging the gap between deterministic laws of physics and the randomness and complexity observed in the cosmic structure, chaos theory enriches our comprehension of the universe's origins, offering a nuanced narrative of creation that embraces both order and chaos. Quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one, no matter the distance, instantly correlates with the state of another, presents fascinating implications for the universe's first moments. In the densely packed nascent universe, where conditions were extreme and matter was in an intensely hot, dense state, the principles of quantum mechanics would have played a crucial role. During this period, particles were so closely intertwined that quantum entanglement could have occurred on a scale incomprehensible in today's universe. This entanglement at the dawn of time could suggest that the early universe was a highly ordered state, with particles and forces intertwined in a complex quantum web. The implications of such widespread quantum entanglement in the universe's infancy are profound. It suggests a level of coherence and interconnection that could have influenced the universe's subsequent structure and evolution. For instance, this interconnectedness could help explain the uniformity seen across vast distances in the cosmic microwave background radiation, as entangled particles would retain their correlations no matter how far apart they become as the universe expands. Quantum entanglement in the universe's first moments might also provide insights into the seamless fabric of space-time and the unified forces during the universe's unification epoch, potentially offering clues to bridging quantum mechanics and general relativity, two of physics' most fundamental yet seemingly incompatible theories. Understanding the role of quantum entanglement at the beginning of everything could thus be key to unlocking mysteries about the universe's foundational structure and the laws that govern it. The quest to understand the universe's origins is not merely an academic pursuit. It carries profound implications for understanding our place in the cosmos. As we peel back the layers of cosmic history and uncover the mechanisms that led to the universe's birth, we're also engaging in a deeper, philosophical inquiry about existence itself. The realization that our universe may have emerged from a singularity, expanded through processes like inflation, and evolved over billions of years to foster galaxies, stars, planets, and life, underscores the interconnectedness of all cosmic phenomena. This narrative places humanity within a vast, dynamic cosmos where we are but a fleeting moment in its extensive history. Understanding the universe's origins also confronts us with the sheer scale of the cosmos and the fundamental forces that govern it, challenging our anthropocentric viewpoints and highlighting our shared cosmic heritage. It fosters a sense of cosmic humility, acknowledging that our existence, while seemingly insular and significant on a personal or planetary scale, is intertwined with the universe's broader, complex processes. Moreover, this quest for cosmic origins invites us to reconsider the meaning of life and our responsibilities as conscious beings within this immense cosmos. It prompts us to think beyond our immediate concerns, contemplating our legacy and impact in a universe that surpasses our understanding. How do you think the universe came to be? Has it always been here, or are there other unknown forces involved? Let us know your thoughts in the comments below.